So what we're going to look at now is finding the area between two curves. We know how to take the integral of the area under a curve, but the area between the two curves we have to look at. It's not as hard as it sounds. If you were to imagine that between A and B, the area that is filled in underneath g of x goes all the way to the x-axis, and h of x shares that same region here. Ultimately what we're doing is taking the area of the curve, the total area under the curve of g of x, which goes all the way down to the x-axis, and we're subtracting off the area that is shared. So you can write it like this: the integral from a to b of g of x, subtract off the area from a to b of h of x, the integrals, right? Or another way that you can write it is you can put into 1 and have it as the two functions subtract each other. Now what's very useful for this section is obviously graphing it so you can see which graph is higher or above the other graph, and any intersection points. Now this one doesn't have any points that intersect, but there will be some that will. For instance, if I was looking at these two curves, your g of x and h of x, they cross at a point C. So one goes above, the g of x goes above from C to A, but h of x goes above from C to B. So when you write your integral, it's going to go from A to C. C is your intersection point, and it's the point where they change from one being above and the other one being above. So then we have here where g of x is above, subtract h of x where it's below, to here where h of x is above and g of x is below. So you can see the order here is changed based on which one is above. Another type of scenario we could have is where we have a region bound by 3 lines. Here you can see, or graphs or whatever, here's one graph, h of x, here's another one, f of x, and here's another one, g of x. The region that is bound between all 3 of these are based on intersection points between 2 pairs, or 2 lines, but we also have to consider where one goes from being above to below and above to below. So not only do we have to find the 3 intersection points, we also have to figure out where one is higher than the other. So this intersection point is important because it kind of splits our graph as to which one is the upper function. Here f of x is your upper function, here h of x is your upper function. So this is quite important. Then if we look at this one is the lower function for both. So again, this is one of our intersection points here. So from A to B, f of x is higher than g of x, so f of x minus g of x. And we're going to add the other area that's on the other side from B to C, based again on this intersection point where it goes from having h of x above g of x. We're also going to look at how a region is going to be integrated along the y-axis. So the previous examples were based on the x-axis. Find the area above or below the x-axis. Now we're going to be looking at a function in terms of y. So now it's going to be integrated along the y-axis. So if I have a function in terms of y, I can take the integral in terms of y along from A to B. Now how that's important is now if we want to find the area between 2 curves, these 2 functions are in terms of y. So the same ideas apply. It goes from A to B, the more positive, the more rightmost graph, subtract the most leftmost graph. So same idea, if you were to draw it all the way to the vertical line, you would take your g of y and subtract off the shared area of h of y, which is what we've done right here. So a lot of this section is graphing and identifying which function is either more positive, higher, or to the right and finding intersection points of two functions, so then you can integrate it appropriately.